Welcome back to G Fun Facts Online. The year is 2026. Nearly 3 decades have passed since the universe shocked us. Back in 1998, 2 independent teams of astronomers observing distant Type Ia supernovae, which are our cosmic standard candles, expected to see the expansion of the cosmos slowing down. The logic was simple physics. The mutual gravitational pull of all matter should act as a gradual break. Instead, they found the exact opposite. The universe was not breaking. It was accelerating. The fabric of space-time was being stretched apart by an unknown, invisible agent that has since been labeled dark energy. Today, dark energy is the dominant component of the standard model of cosmology, known as Lambda CDM. It accounts for roughly 68% of the total energy budget of the universe. It is mathematically tidy, represented by the Greek letter lambda in Einstein's field equations. This is the cosmological constant, describing the inherent energy of empty space. But there is a massive problem. Despite its observational success, lambda is theoretically arguably the worst prediction in the history of physics. Quantum field theory suggests the vacuum of space should be fizzing with energy roughly 10 to the power of 120 times stronger than what we observe. If lambda were truly that strong, the universe would have ripped itself apart explicitly moments after the Big Bang. Furthermore, we are currently facing the Hubble tension. This is a statistically significant discrepancy between the expansion rate measured locally using supernovae and the rate predicted from the early universe using the cosmic microwave background. The two numbers do not match, and the gap is only widened with the precision data from the James Webb Space Telescope and the Euclid mission. This crisis suggests that Lambda CDM, for all its utility, may be a mirage. The acceleration might not be due to a constant energy of the vacuum. It might be a sign that gravity fails on large scales, or that our fundamental assumptions about the universe's geometry are wrong. Today we are going on a comprehensive journey into the alternatives to dark energy. A tour of the exotic, the revolutionary, and the terrifying ideas that seek to dethrone the cosmological constant. Let us begin with the first major alternative, the dynamic universe, specifically quintessence and scalar fields. If the vacuum energy is not a constant, cosmologists ask, perhaps it is a fluid, a dynamic changing field that permeates the cosmos. In particle physics, we are familiar with scalar fields. The Higgs field is the most famous example. The question becomes, what if the acceleration is driven by a scalar field that slowly rolls down a potential energy hill? This class of models is collectively known as quintessence, named after the classical fifth element. Unlike the cosmological constant, which has a fixed equation of state parameter of -1, quintessence models propose a parameter, denoted as W, that can vary with time. The field acts like a fluid with negative pressure. If the field rolls slowly enough, satisfying a slow roll condition similar to inflation theory, it mimics a cosmological constant closely enough to drive acceleration, but allows for subtle variations over cosmic history. The beauty of quintessence is that it alleviates the fine-tuning problem. In some versions, known as tracker models, the field naturally evolves to track the radiation and matter densities for much of the universe's history, before eventually dominating. This makes the current era of acceleration less of a bizarre coincidence and more of an inevitability. However, if we tweak the mathematics of quintessence, we encounter a terrifying possibility. In standard physics, kinetic energy is positive, but if one postulates a scalar field with negative kinetic energy, the equation of state parameter W can drop below -1. This is phantom energy. In a phantom universe, the energy density of dark energy increases as the universe expands. The acceleration does not just continue, it goes into overdrive. Eventually, the repulsive force becomes so great that it overcomes all bound structures. This leads to the big rip. First, galaxy clusters are torn apart. Then, individual galaxies like the Milky Way dissolve. Solar systems become unbound. Finally, in the last moments, stars, planets, and even atoms are ripped asunder. Space-time itself shreds. While current data from the Euclid satellites slightly disfavors deep phantom regions, the error bars still allow for a W parameter hovering dangerously close to -1.03. Related to this dynamic view is the concept of early dark energy. To solve the Hubble tension, the mismatch between the expansion rate of the early and late universe, theorists have proposed that a form of dark energy existed briefly before the epoch of recombination, which is when the cosmic microwave background was released. Early dark energy would have added an extra kick to the expansion rate in the infant universe, changing the size of the sound horizon, which is the ruler we use to measure cosmic distances. By shrinking this ruler, early dark energy forces us to recalibrate our calculations of the modern Hubble constant, potentially bringing the Planck satellite data into agreement with local supernova measurements. As of 2025, early dark energy remains one of the most promising, though hotly debated, solutions to the crisis in cosmology. Now let us pivot to a completely different perspective, the lumpy universe, or inhomogeneous cosmology. Perhaps the most radical alternative to dark energy is the suggestion that it does not exist at all. The standard model relies on the Copernican principle, also known as the cosmological principle. This is the assumption that, on large scales, the universe is homogeneous, meaning the same everywhere, and isotropic, meaning the same in all directions. We treat the cosmos as a smooth fluid. But we know this is an approximation. The universe is actually a cosmic web of dense galaxy clusters, filaments, and vast, empty voids. What if the averaging is wrong? Thomas Buchert and others have long argued that the back reaction of small-scale structures on the large-scale metric could mimic acceleration. General relativity is a nonlinear theory. This means the average behavior of a complex system is not necessarily the same as the behavior of the average system. As structure forms, the expansion rate in voids becomes faster than in filaments. If we measure the universe's expansion by looking through these voids, we might incorrectly infer a global acceleration driven by dark energy, when in reality, we are just seeing the complex variance of gravity in a lumpy universe. Professor David Wiltshire from the University of Canterbury champions a specific inhomogeneous model called timescape cosmology. In this view, clocks run at different rates, depending on where they are. A clock in a deep gravitational well, like a galaxy, ticks slower than a clock in a cosmic void. Since we are observers in a galaxy, we are looking out at a universe dominated by volume, meaning the voids. We are subject to a calibration error. We assume time flows uniformly. If we correct for the fact that the universe's expansion is dominated by voids, where time flows faster relative to us, the apparent acceleration vanishes. The universe appears to accelerate only because our local clocks are slow relative to us. The apparent acceleration vanishes. The universe appears to accelerate only because our local clocks are slow relative to the cosmic mean. Recent 2024 studies analyzing Pantheon plus supernova data have provided fresh statistical support for this view, suggesting the lumpy universe fits the data just as well as Lambda CDM, without requiring a mysterious new energy fluid. A major development in the mid-2020s has been the local void theory. In 2025, researchers led by Dr. Indranil Banik presented compelling evidence that the Milky Way resides near the center of a colossal underdensity, a supervoid spanning nearly 2 billion light-years. If we live in a bubble that is 20% emptier than the cosmic average, matter outside the bubble would pull on us more strongly than matter inside. This would cause the local region to expand faster than the global average. This bulk flow would contaminate our measurements of the Hubble constant. The resolution to the Hubble tension here is that we are measuring the fast expansion inside the void and comparing it to the slower expansion of the global universe seen by the CMB. If the local void model holds up to scrutiny from the full Euclid data release, dark energy might simply be an artifact of our unique, lonely location in the cosmos. But what if the universe is not filled with invisible fluid, and inhomogeneities aren't enough to explain the data? We must face the ultimate possibility. General relativity breaks down on cosmological scales. General relativity has been tested with exquisite precision in the solar system, but applying it to the entire universe is a strictly chaotic extrapolation. Modified gravity theories attempt to rewrite the laws of gravity to produce acceleration naturally. The simplest modification is f of r gravity. Einstein's action depends on the Ricci scalar r, a measure of space-time curvature. In f of r theories, one replaces r with a complex function, f of r. By tuning this function, one can generate a force that mimics dark energy on large scales, but disappears on small scales, recovering Newton's laws where we live. This is often achieved via the chameleon mechanism. This involves a scalar field that becomes heavy and short-ranged in dense regions like the Earth, hiding itself from our experiments, but becomes light and long-ranged in the empty vacuum of space, driving cosmic acceleration. Another contender is massive gravity. Standard general relativity assumes the graviton, the carrier of gravity, is massless. If the graviton has a tiny, non-zero mass, gravity would weaken over large distances. Massive gravity theories, and their cousin bigravity, which involves interacting metrics, can naturally lead to self-accelerating solutions. Historically, these theories were plagued by ghosts, which are mathematical instabilities implying negative probabilities. However, recent formulations such as DRGT gravity have exorcised these ghosts, making massive gravity a viable, albeit complex, contender. A growing area of interest in 2026 is Finsler gravity. This approach extends the geometry of space-time itself. In standard general relativity, the distance between points is defined by a metric in Riemannian geometry. Finsler geometry allows the distance to depend not just on position, but also on the direction of the observer. Recent papers, for example from the ZARM Institute, suggest that applying Finsler geometry to the cosmos naturally produces accelerated expansion terms in the equations without adding dark energy. It implies that the vacuum has a geometric orientation or structure that standard general relativity ignores. Beyond modifying gravity, there is a philosophical shift towards emergent and entropic gravity. This is the idea that gravity is not a fundamental force at all. Instead, it might be an emergent phenomenon, like heat. Thermodynamics describes the behavior of gas, but heat does not exist for a single molecule. It emerges from the statistics of many. Erik Verlinde from the University of Amsterdam proposed that gravity is the result of entropy changes in the information stored on the fabric of space-time. In entropic gravity, when matter moves, it changes the information content or entropy of the vacuum. The universe resists this change, creating a force we perceive as gravity. Verlinde's equations naturally derive an extra term that acts like dark matter on galactic scales and dark energy on cosmic scales. In this view, dark energy is simply a manifestation of the entropy of the universe, pushing bound explicitly against the horizon. It solves the magnitude problem elegantly because the acceleration is linked to the area of the cosmic horizon, naturally producing the small value of lambda we observe. Related to this are the holographic dark energy models. Based on the holographic principle, which states that the information of a volume is encoded on its boundary, these models posit that the energy density of the universe is limited by the size of the future event horizon. This constraint forces the vacuum energy to evolve dynamically, driving acceleration. Finally, we must touch upon string theory and the swampland. For years, string theory struggled to produce a universe with positive vacuum energy like ours. It prefers anti-de Sitter space, which has negative energy. This difficulty led to the swampland conjectures, championed by Qumran and Vafa. The conjectures suggest that a constant stable de Sitter vacuum, which is standard dark energy, is mathematically impossible in a consistent quantum gravity theory. It resides in the swampland of failed theories. If the swampland conjectures are true, dark energy cannot be constant. It must be a rolling field, like quintessence, that will eventually decay. This predicts that the acceleration of the universe is temporary. In the deep future, the field could roll into negative values, causing the universe to stop expanding and recollapse in a big crunch, or transition into a completely different state of physics. We are currently in the golden age of observational verification. Euclid, launched in 2023, is currently mapping billions of galaxies to create a 3D map of the universe. Its primary goal is to measure the equation of state W with high precision. If Euclid finds that W is not equal to -1, or finds that W varies with time, the cosmological constant is dead. DESI, the dark energy spectroscopic instrument, is measuring the baryon acoustic oscillations with unprecedented accuracy. And the Vera Rubin Observatory is fully coming online in the mid-2020s to find hundreds of thousands of supernovae. As we stand in 2026, the consensus is fracturing. The Hubble tension has refused to vanish, acting as the loose thread that might unravel the Lambda CDM sweater. While the cosmological constant remains the simplest fit, it is the most intellectually unsatisfying. The alternatives, from the rolling fields of quintessence to the geometric rethink of inhomogeneous cosmology, offer a glimpse into a deeper reality. They suggest that the dark energy we detect might be a shadow of higher dimensional physics, a statistical illusion of a lumpy universe, or a sign that the laws of gravity effectively change when we look at the cosmos as a whole. We may soon discover that the dark sector does not exist. We might simply be learning, for the first time, how gravity truly works.